There are two main libraries for property-based testing in Haskell. They are QuickCheck and Hedgehog. And they differ primarily in how they shrink. In QuickCheck, you have to write your own shrinker. And in Hedgehog, you don't. In Hedgehog, when you write a generator, you get a shrinker implied. And that's often called integrated shrinking, and it's quite nice. But one problem is that it doesn't work so well with monetic bind. So the last few months, I've been working on a new library called falsify, which gives you integrated shrinking, but in a way that does work across monetic bind, inspired by the hypothesis library in Python. Oops.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, this show is live streamed, so we invite you to submit questions or comments in the chat, and we will try to show them on screen and to discuss them.
Yeah. So let's start with a simple example. Suppose that we are testing a function. And just for the sake of a simple example, let's say that we have an idea and we say maybe we have a clever idea. We think we're being clever, and we have an idea for a faster way to increment a number by 1. So we're going to write a function from a number to a number, from word to word. And the idea, the intention is that this function is going to increment the number by 1. And so the way that we're going to do it is we're just going to OR this number with 1. So we're going to set the least significant bit of this number to 1. And we think we're being clever. We think we have found a fast way to increment a number. So this is the function that we might want to test. And of course, we're good software engineers, so we write a test for this. And the way that we would write that in falsify, it's something like this. We're going to write a property. That property is going to look something like this. We're going to generate a random input for the function, right? So this is key to property-based testing. Rather than calling functions on specific inputs and checking for specific outputs, instead, you generate random inputs, and then you verify that the input and the output are related in some way. So here we're going to generate a random word, and for the sake of this argument, this demonstration, we just use a built-in from the library called integral, which can generate any value of an integral type. And that wants a range, and we just say, let's generate a random number between 0 and 100. Right, so now x here is something of type word, or really any integral value. And then we have an assertion. That assertion says that if we increment x by using this function, the result should be x plus 1, right? That's the property that it should have. So falsify uses a small domain-specific language for predicates to express these kinds of things. So we're saying the expected value is x plus 1, and the actual value here is, well, the value that we get from running our function, right? And these two things should be the same thing.
So basically, you're establishing an equality between, or a desired equality between x plus 1 and incr of x, and you're labeling these two results presumably so that these labels can be used in potential error messages, right?
Yeah, that's exactly right. Yeah, so these labels will, if the property does not hold, then these labels will be used to give us a better type error. Rather than just saying property false, it will give us something information about what actually happened. But let's do that. Let's actually run this property. So falsify is integrated with Tasty. It could also be integrated with HSpec or other things. Currently, it just provides Tasty support. So, and it looks just like any other kind of Tasty property. So you say test property, you give it a name, and then the property that we want to test. And then I could run this guy, and I can just say run this and give it this property. And now here's the test output, and the test fails, right? It tells us fail. And it gives us a bunch of information. So let's look at the information that it's giving us. First, the log here is telling us which values were generated during this test. Right? Every time that we call gen, we generate a new value, and it will be added to the log. And in this case, it tells us that the value that was generated was 1. Right? So x here is 1. And then, like Andres said, we have this information in the predicate, right? So we have expected and actual. The expected value, well, we generated 1, right? So expected was 1 plus 1 equals 2. Fine. Okay, so we expected 2. And the actual value was 1, right? Because what happened well, we ORed 1 with 1, which is just equal to 1, right? So this is actually not a good way to increment the number by 1, which is kind of obvious, but just for a simple example. Now, one thing that's of interest here is that we got the counterexample 1, right? 0 is not a counterexample, right? 0 or 1 will be 1, so it would work for 0. It doesn't work for 1. And it's the smallest number for which it doesn't work, right? So even though we generate an arbitrary number in this range, the counterexample was 1. And that's not a coincidence. It doesn't matter how often we run this test, we will always get 1, even though we always generate a random value in this range. And that works because we generate a random value first, and then it starts to shrink. And actually it tells us how often it was shrinking this number here, even though we did not write a shrinker, right? So when you write a generator in falsify, like in Hedgehog, you get a shrinker sort of implied. All right. That's by means of an introductory example. So what sets falsify apart from QuickCheck and Hedgehog is how this shrinking actually works. So that's what I want to focus on. I want to run through some examples of generators and talk about how they shrink. So let's look at a simple example. Let's write a generator which produces an arbitrary value below some sort of maximum. And let's only use the primitive generator that the library offers. So we want to write a generator that gets a maximum and produces a number below that. And so what we're going to do is we're going to define this in terms of prim. Prim is a generator from the library which produces an arbitrary number in the full range of word 64. Right, so now we need to have some way of turning this full range into the much smaller range that we're interested in, right, between 0 and n. And one way you might do that is by simply taking the modulus, right, the remainder. So we take this primitive value p that prim generated, we just turn it into a word by calling from integral on it, and then we call mod n. And this might be a way that we can squash the range from the full range of word 64 to something much smaller. And now we could rewrite our property here using this new generator. I hope you believe that. But I want to think a little bit about how this guy is shrinking. So, and in fact, rather than just thinking about it, let's test how it's shrinking, right? John Hughes, who's the father of property-based testing, always likes to say, don't think too much, right? Write properties that express things and then just test them, right? Let the testing framework do your thinking for you. So, what would shrinking a value look like? Well, presumably the value should get smaller, right? That seems like a reasonable value property that shrinking should have for values. So let's write a property that does precisely that. Right, so we have another property, oops, which I'm going to, this is going to test the shrinking behavior of below. And it's going to use a combinator from the library for that. And this combinator takes two arguments. It takes an argument, which is a relation that relates values before and after shrinking. Right? And for numbers, we hope that the number before shrinking should be smaller, should be larger than the number after shrinking. Right? So that's the relation that we're interested in here, greater than or equal to. And then it takes a generator. And in this case, the generator that we want is below. Right? Actually takes a property. And since shrinking only happens when properties fail, this property should fail with something, right? In this case, it's going to fail with the value produced by below. Right? And now, so we're failing with a particular value, and then we're asserting something about how that value changes as we shrink. Right, so now we have another property that we could test. So let's do that.
Below shrinking 1.
Sorry, yes, thank you. And it tells us, it gives us a counterexample, right? It says that this property is not true. And the counterexample here is, well, we were shrinking from 37 to 83. And indeed, that is not the shrink step that we were expecting, right? The number got bigger, not smaller. So what happened? And it's a little bit difficult to see what's happening from here, right? The log tells us that the value of x that we generated before shrinking was 37 and after was 83, but we already knew that, right? The log is not really telling us anything new. So we need to dig a little bit deeper. We want to know what happened with this value of prim and how we turned that into the number that below generated. So we could write another property here that sort of splits these two things apart, right? So that we first call prim and then do the rest of the logic. And we are still, like the top level property is still the exact same thing. But rather than calling below directly, we're just going to call prim. And then we're just going to let x be equal to this expression, right? The exact same thing that that we had before, right? So we're not changing the logic. We just want to basically add some debugging information, right? And then we still fill with x here. Oh, sorry, Jen. Yeah. And so now the key difference here is that since the log always tells us what the values are being generated, we can now see what prim gives us, and we can see what below gives us derived from prim, right? That's the difference. So now if we run this property, we get more information. So the log now gives us the value generated by prim, right? And it has this enormous number here, which was shrinking to this much smaller number here. So it's about roughly half, which is to be expected because prim is doing binary search. Okay, but now if we look at the final two digits, it's 04 in the first one and 52 in the other one, right? And that's the one that results that we're getting, right? We're taking modulus 100, so we get the last two digits. And of course, if a large number is shrinking, it does not necessarily mean that the last two digits also must be shrinking. So that's what the problem is with this generator. So yes, we get a shrinker automatically implied, but that shrinker might not necessarily be a very good one, right? So people sometimes say integrated shrinking gives you shrinking for free, and that's actually not true for any approach, right? Whether it's hedgehog or hypothesis or falsify, you always need to think a little bit about how shrinking works.
Right. So you want to instead do something where the largest possible where it gets to exactly to the upper bound, and the smallest possible where it gets exactly to the lower bound, and everything else gets kind of uniformly in between, I guess.
Yes, exactly. Right. We have this full range of word 64. We kind of want to squish it into the much smaller range that we have. And so that if we shrink in that larger range, we shrink accordingly in the small range. Precisely. So let's see how we could do that. One option, and there's many ways that we could do it, but one option is to first generate a fraction. So we're going to generate a fraction between 0 and 1. And again, we're going to use prim to do this. Right, so prim gives us, again, an arbitrary number in the full range of 464. So we now need to turn this into a fraction, right? And that's actually fairly simple, right? We just divide this by the maximum number that we can get, right? So we have some x, we take x, turn it into a double, and then we just divide it by the maximum number that we could possibly get. Right, and so if this number is 0, then this will be 0, and if this number is max bound, the maximum number that is possible, it will be 1. Right, and now this fraction is very useful, right? We can use this as a building block in lots of generators, but for example, we can use it as a replacement for our below. And I'm calling it at most because there's minor differences in bounds here, but not so important. What we're going to do, so this generator is going to generate a value that is at most x. Right, somewhere between 0 and x inclusive now. So we're going to do that in terms of fraction. Oops. So we take this double and we need to turn it into a word now. And that sounds simple, right? We have the full range and we just multiply this by the fraction, right? And then round it again. So this is a way to do precisely what Anders was suggesting earlier, right? We were taking this big range and we're squishing it down into the smaller range.
Yes.
So was there a comment?
No, I was just acknowledging. Yeah.
All right.
Yeah.
But now if we take the same property that we had before, right, the shrinking property, but now rather using below, we use at most, and we test it again, right? And we run this. Now this property passes, right? It told us it ran 100 tests what is happening underneath the hood. It's generated an arbitrary value, it shrinks it, does the property, yada, 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 right? And it's doing this over and over and over, and it didn't find any counterexamples. Right, so this is a better way to write this particular generator. Okay. Let's move on to something slightly more interesting, which will also allow us to talk about the difference between hedgehog and falsify. Right. So far we've seen that when we write a generator, we get an implied shrinker, but we get that in hedgehog too. Right. So let's look at the differences now. So in particular, let's think about how we might generate lists. And the simplest way that you might do it is actually working relatively well. Not great, but better than you might expect, perhaps. So what we need to do, right, we are going to take a maximum length of the list that we want to have and a generator for the elements, and we're going to produce a generator for lists. And what we're going to do is we're just going to generate an arbitrary actual length between 0 and the maximum, and I'm just reverting back now to the combinator from the library. We could have used utmost. The library behaves a little bit better, it's a little bit more performant, but doesn't really make a difference. And then we just call our generator that number of times. N. So we just pick a random length and we just call the generator n times. Very simple. So let's see how this behaves. Suppose that we want to test that every element of every list is always equal to each other, right? A list only has like one type of element. So we could write that property as saying if we take the nub, right, which takes all the unique elements in the list, that length of that nub is at most 1, right? So it could be 0 if the list is empty, or it's 1 if there's more elements, but they're all equal to each other.
Okay, yeah. So hopefully that should be wrong, right?
Yeah, right. We should expect this to be wrong, right? Otherwise, right, exactly. Otherwise, we would not be generating very interesting lists. So let's try. Let's use our list generator. Say that we have a maximum length of 10, and now we need the generator for the elements, and let's just generate booleans.
What does the false mean?
Yeah, the false is an argument. So and it tells us what we want to shrink towards. So bool of false is a generator that produces a bool and shrinks towards false. Bool of true is a generator that produces a bool and shrinks towards true. Right?
Okay.
All the generators in the library take in the direction as argument. Like they never assume that you mean one thing or the other. All right. So now we want to check that this property holds, right? That all equal holds, and hopefully we'll get a counterexample. Right, so we say that some property should hold, which property? Well, this all equal property, and it should apply to x's. And so x's should satisfy the property all equal. So this is kind of a complicated way of saying all equal x's, but again annotated with additional labels so we get better information. Okay. So let's run this test. All equal 1. Right, and we get a counterexample, right? False, 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 true, which indeed has more than one value, right? So it is indeed a counterexample to the test. But it's not a very nice counterexample, right? It's not minimal.
Yeah.
Right, we have 4 elements.
It's a 4-element list rather than...
Yeah, why? I mean, all we need as a counterexample is a 2-element list, right? We need 2 elements which are different from each other, right? That will be the minimal counterexample.
Yeah.
But we didn't get that. Why not? Well, if you think about it, how is this guy shrinking? Well, this number can shrink, this length, the length of the list, can shrink, or the elements can shrink, right? But if the length of the list shrinks, all that's happening is that we take a prefix of the list, right? If we go from 4 to 3, in this example here, right? Currently we're 4. If we go down to 3, look what happens. We have a list false, false, false. We would end up with a list that only has the element false in it, and so would no longer be a counterexample, right? It would indeed be an example of a list where we only have one type of value, one kind of value, one value.
By the way, quick question.
Yeah.
I mean, quick check additionally has this property also that it starts generating small elements and then it generates larger ones, but
Yeah.
guess that's not the case here, right?
That is not the case in falsify. Yeah. QuickCheck does this by having a sort of an implicit size argument that is propagated around. I've never been a big fan of it because that size argument is kind of weird. It's hard to interpret. It's not composable very well. And so falsify does not do that. You can do it if you wish, but yourself, but it doesn't do it by automatically.
Okay.
Yeah. So we rely on shrinking to get this.
Yeah.
All right. So one problem is that it's not shrinking very well because it can only shrink to the prefix of the list. But there's something else that is of interest here. If I run this with a particular seed, I mean, there's this one particular test case that I just happens to illustrate the property that I want to have. Right, I've now run the library in verbose mode, which means that we are seeing every single shrink step. And we start with this big long list here. Fine, okay. We took a prefix of it. Okay, fine. And then what's happening here? Now here we can see that we shrunk one of the elements, right? This true went from true to false here. And then we shrunk the element of the length of the list again. Right, in this case, we are ending up with a nicer counterexample, false, true. What's of note here is that we are flipping back and forth between shrinking elements of the list and shrinking the list length. That cannot happen in Hedgehog, right? Whenever you have monetic bind, all right, there's monetic bind here in the middle, right? This big long list, this big bar here, we have monetic bind. We're binding something and then we're using it. Every time that you have monetic bind in Hedgehog, or in any library that uses that sort of approach, indicator shrinking, introduces a strict dependency. First shrink this, then shrink this. So in Hedgehog, once we start shrinking elements of the list, we would never go back and shrink the list length again. In falsify, you can. We can go back and forth over this binary, no problem, right? And this is what hypothesis told us how to do. But I must say that the actual theoretical foundations that underlie falsify are quite different from hypothesis. Inspired by, but certainly quite different. I won't have time to talk about that now, but I've submitted a paper about this, and hopefully that will be accepted. So once it is, you can read that for more details. Right, so I want to show you how to write this better, and I also want to show you two other things. So I won't show you all the details. I just want to give you some intuitions here. So the better way to write a list generator, of course, there's one in the library, right? You could just use a standard combinator for lists. I mean, it actually takes a range for lists. I mean, that's much more fancy than the one that we're doing here. But the point is to explain the principles here. So if we want to have a better list generator, what you could do is you could write a generator for maybes here. And maybe takes a generator and produces maybe an A, right? How does it do it? It first produces a bool, shrinking towards false. If it's true, it calls the generator and wraps it in just, or otherwise it returns nothing, right? So since this bool is going to shrink towards false, this whole thing is going to shrink towards nothing.
Yeah.
And now we could write a better list generator by simply, we don't even need to pick a random length anymore now. We just have a maximum length. We call replicate again like we did before, but now on maybe of G, right? So now all of these values are maybe nothing, just nothing, whatever, right? And then we just take the just values out of it, right? And now as this starts to shrink, individual elements of the list can start to shrink towards nothing, meaning that we can drop arbitrary elements from our list.
That means that it's very unlikely that you'll ever get something that is even close to the maximum length, right?
Yeah,
I mean,
that's completely right. That's the downside of this particular implementation. The version in the library does not have that downside. It takes some other clever things to avoid that problem, but yeah, that's right. Right. Okay. I want to show you two other things. First, I want to show you that we can generate.
Keep in mind that we have officially only 5 minutes left.
Yes,
but,
yes, I'm aware. Yeah.
Okay.
So suppose that we have the property that if we first map and then filter, that should be the same as first filter and then map, right? If you think about it, that property is not true. But if we want to test that, then we need to generate an arbitrary list an arbitrary function f and arbitrary property p, and which we can do. But I'll just show you what that looks like. So the library has this function called fun, which is used to generate arbitrary functions, and it generates an arbitrary function, which is an infinite object, right? This is an object that describes the function, which has an output for the function for every possible input, of which there are infinitely many, right? And it generates random outputs using the generator that you give it, right? Which in this case is prim. So we generate a random function from word to word, then a random predicate, which just from random booleans. We then generate a random list, and then we check the property, right? The left-hand side is this guy here, and the right-hand side is this guy here. And so we could call this and it gives us a counterexample. Right, and the counterexample is we generated which list? The list 0, 9. The function maps everything to 0, and the predicate is true for 9 and false otherwise. So let's think about that. This is the list 0, 9. If we first map the function over it, we get 0, 0 because the function maps everything to 0. And then we filter. The filter is only true for 9, so that's true nowhere. So the left-hand side is the empty list, which is what we got here. And on the other hand, if we first filter, then we have a 9 in here, so we keep the 9, and then we map, turning that 9 into a 0. Right, so we get the list 0. So this property is simply not true. Right, and I just wanted to point this out, that you can do this. You can generate arbitrary functions, when you can generate infinite objects. Right, everything in falsify is completely lazy, so that you can do things like this.
So, and functions are smaller if they have fewer exceptions from the default, right?
Yeah, that's what it means to shrink a function, right? So a function is basically has this value for every input and a default. And how do you make it smaller? Well, you throw out everything that's not the default, right? And so the fewer exceptions, like Anders said it, the smaller the function is. Yes, exactly. And at the end, the function will be finite. Everything else, there's only a finite number of exceptions to the default.
But we still get 9. What was it?
Yeah. Yeah.
So that is not minimal in a way, right? 9.
That's not minimal, right? This 9 appears, and the reason is that this is a dependency, right? We have a 9 here, and we have a 9 in the list. And if we wanted to shrink this 9 would have to become a 1 here and here at the same time, right? And that does not happen. But that is true for any property-based testing library, right? That's proper, Quick Check, Hedgehog, whatever. That's always true. So yeah. There are ways to fix that, but that would require a bit more user intervention. Okay. Final thing I want to show you. Suppose that we have this generator, and this generator looks a little bit strange maybe, but bear with me. Suppose that we're going to generate either a letter or a number. So we have some generator for letters, a generator for numbers, we generate a Boolean. If the Boolean is true, we return left the letter, otherwise we return right the number, right? And now we have some property of this guy, which says that any value generated by this generator, if it's left, then the letter should be A. If it's right, then the number should be 0. Right? And this is again another example of a property that should clearly not be the case. So if we run this, then we're going to get a counterexample, as expected, right? Because clearly this is not always true. But the interesting thing is that the counterexample is not great. Sometimes it's left, sometimes it's right. And if you think about this, ideally, this bool shrinks towards false. So the smallest counterexample, right? This should always be right. It should shrink towards right. The problem is that suppose that we are currently generating a left value, right? So the Boolean is currently true. Then this number is unused. Therefore, it can shrink trivially, right, without affecting the property, towards its minimum value. Its minimum value is 0, right? This generator shrinks towards 0. But 0 is not a counterexample to the property. Right? So that's why this is not working. If we currently have a left value, that number shrinks towards 0, and then we can no longer shrink the Boolean because we would not have a counterexample anymore. So the last thing that I wanted to say is that gen is not just a monad, it's also a selective functor. What that means is that we have a function of this type. And this is what a selective functor has as primitive, right? It allows you to choose between things, right? So you could think of this as being gen, right? I mean, this is true for any selective functor, but in particular, it's true for gen. But now, this is a better way to choose between generators, right? We should write our example here as, if the Boolean returns true, then return the left generator, run the left generator, otherwise run the right generator. And what selective functors do, they selectively allow you to omit effects. And in our case, we're taking advantage of this to selectively omit shrinking. Right? And now this guy, we can have the same property here as we had before. It's exactly the same property, except using this new generator here. And if I run that, then we will always get a right value no matter what, no matter how often we run this thing, right? This now shrinks properly. So the moral of the story here is that do not generate values that you don't use. If you need to conditionally run a generator, take advantage of the selective interface. That's, by the way, is a deviation from what hypothesis does. In hypothesis, you don't have such a thing, but in hypothesis, you just use a normal if, but then the generators can't shrink independently from each other, right? So you actually get much more shrinking than you get here. But for that, the details will be in the paper as well. All right, that's really all I wanted to show to you.
Do you have any experience in terms of, like, if you actually use this for your own application to test your own code, then, like, do you mostly just write generators and directly in terms of the standard library, or do you have to do a lot of work along the lines that you now outlined to build your own generators? Like,
no, in most
building
cases,
blocks or
yeah. No, that's a good question. In most cases, I don't worry. We don't have to worry about this. In most cases, for most generators, you just build them in terms of the building blocks of the library offers, and that's fine, right? Not always, but often, most of the time, that's okay. The case. Yeah, I just focused on the more, like, those building blocks themselves are tricky to build, and sometimes you need to write your own. And so I focused on that because it allows us to describe how this library is different from Hedgehog. But of course, in reality, most of the time, you don't have to worry about this.
Okay. No, there haven't been any questions in the chat now, and I think I've already been asking quite a few of questions on my own. So, but let me just say that you're most welcome to also, if you're watching this later, to just leave additional questions in the comments below the video so that we can answer them later. And yeah, thanks for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe, and leave any other comments you might have as well. And yeah, hope to see you again in 2 weeks.